Imagine CPU wants to send some data to memory, but how do they actually communicate with each other? But communication is not as simple as just sending data. The CPU needs to know how to send the address, how to send the data, and whether the memory is ready to receive or not. We also need a way to know when the entire transaction is complete. So ultimately, we need a set of clear rules for communication between different components. This is where AXI comes into picture. AXI provides a set of rules that allows different components to communicate. Before going further, let's understand two important roles in AXI, the master and the slave. The master is a component that initiates a transaction, while the slave is the component that responds to that particular transaction. Now let's understand one of the most important concepts in AXI, the valid and ready handshake. In AXI, the sender uses the valid signal to indicate that the information is available. The receiver uses ready signal to indicate that it is ready to accept that information. A transfer happens only when valid is 1 and ready is 1 in the same clock cycle. So in the diagram in the picture you can check actually. So in the first clock cycle the valid is 1 but ready is 0, so there is no transfer. And in the third clock cycle also the valid is 0, ready is 1, but there is no transaction, there is no transfer, right? So the transfer will happen only when the valid and ready both are 1 in the same clock cycle. Now we understood how data transfer works using valid and ready handshake. Let's see how actually AXI organizes communication. AXI uses 5 independent channels. 3 channels are used for write transaction and 2 channels are used for read transaction. Let's now look at these 5 channels more closely. For a write transaction, AXI uses 3 separate channels. First one is a write address channel, which carries the address where the data needs to be written. Second one is write data channel, which carries the actual data. And finally, there is write response channel where the slave sends the status of the write transaction back to the master. Actually, it tells the write happens properly or not, whether it is done or not. Similarly, for a read transaction also there is two channels, a read address channel which sends the address from where it is trying to read, and read data channel through which the slave sends the data corresponding to that particular address to the master. There is no any response channel because CPU knows when it is done, right? So CPU is requesting the read, and when it is getting the data it actually knows that it is done, so it does not need any response. You might be wondering, why does AXI use separate channels instead of sending everything through a single channel, right? So important point is that these channels operate independently. For example, during a write transaction, the master can send the write address first and then write data later. Or depending on when the slave is ready, the write data can be accepted independently from the write address. This means the address channel and the data channel do not have to wait for each other to complete their handshake at the exact same time. This independent communication makes AXI more flexible and helps improve overall performance. Now let's look at a complete AXI transaction and understand the signals involved. A write transaction uses 3 channels as I mentioned. First, look at the write address channel. The master sends the address where the data should be written using the AWADDR signal, and then the master asserts AW valid to indicate that the address is valid and available. When the slave is ready to accept the address, it asserts AW ready signal, and address transfer takes place sorry, when both AW valid and AW ready are high. Next comes the write data channel. The master sends the actual data using W data signal. For example, let's say the data is 4E followed by 4F. The master asserts W valid to indicate that the data is valid. When the slave is ready to accept the data, it asserts W ready. The data transfer takes place when both the W valid and the W ready are high. Finally, we have the write response channel. After accepting the write transaction, the slave sends the status of the write operation using VRES signal. The slave asserts V valid to indicate that the response is valid. When the master is ready to accept response, it asserts V ready. The response transfer takes place when both V valid and V ready are high. So a complete AXI transaction uses three independent channels: AW for the address, W for the data, and B for the write response. Now let's understand another important signal in AXI write data channel, WSTRB, write strobe. So it tells the slave which bytes of the W data are valid and should actually be written. Each bit in WSTRB corresponds to one byte of the data bus. For example, if we have 32-bit data bus, there are 4 bytes, right? So WSTRB will have 4 bits. If the WSTRB value of the WSTRB is 1111, all 4 bytes are valid and will be written. If some bits are 0, the corresponding bytes will not be written. For example, if the WSTRB will have the value as 0111, then the first byte will not be written. Now let's understand one of the important feature of AXI, burst transfer. So in a normal transfer, the master sends an address and transfers one data item. But sometimes the master needs to transfer multiple data items to consecutive memory locations. So instead of sending a new address for every data item, AXI can send the starting address once and then the transfer multiple data items. This is called a burst transfer. Each individual data transfer in a burst is called a bit. Now we understood what a burst transfer is. Let's look at the different types of burst transfer supported by AXI. There are three main burst type. One is fixed, one is increment, one is rep. So in a fixed burst, the address remains the same for every data bit. In an INCR burst, the address increases after each data bit. This is a commonly used when transferring data to consecutive memory locations. In a rep burst, the address also increases, but when it reaches a defined boundary, it wraps around to the beginning of the boundary. So fixed keeps the same address, INCR increases the address, and rep increases the address and then wraps around. Now let's understand the signals that define a burst transfer. AWLEN specifies the number of data transfer or bits in a burst. The actual number of bits is AWLEN plus 1. So AWSIZE specifies the number of bytes transferred in each bit. AWBURST specifies the types of the burst, whether it is fixed, INCR or rep. These signals are sent along with the starting address through the write address channel. Together they tell the slave where the burst starts, how many data bits will be transferred, and how large each bit is, and how the address changes during the burst. Now let's understand another important signal used during a AXI write burst, WLAST. So as we learned, a burst transfer can contain multiple data bits. So WLAST signal is used to indicate the final data bit of a write burst. For example, in 4-bit write burst, the first 3 data bits have the WLAST equal to 0. On the fourth and the final data bit, WLAST is asserted to 1. This tells the slave this is the last data transfer in the current write burst. So WLAST marks the final bit of an AXI write burst. Now let's look at a complete AXI read transaction. First, the master sends the address it wants to read using ARADDR signal. Also, the master asserts AR valid to indicate that the address is valid. When the slave is ready to accept the address, it asserts a ready signal. After accepting the address, the slave sends the requested data using R data. The slave also sends the status of the read operation using RRESP. Remember, it is not a separate channel, it's just a signal. In case of write, we had write response channel, right? So it is not like that. It is not a separate channel, it's a signal only. The slave asserts are valid to indicate that the read data and response are valid, and the master asserts are ready when it is ready to accept them. So a complete AXI read transaction uses two channels, AR for the read address and R for the read data and response. Now let's understand RLAST, which is used during AXI read burst. Just like WLAST marks the final data bit of a write burst, RLAST marks the final data bit of a read burst. In a 4-bit read burst, the slave sends 4 data bits through the R channel. For the first 3 bits, RLAST will be 0, and on the 4th and the final data bit, the slave asserts RLAST to 1. This tells the master that the current read burst has reached its final data bit. Now let's quickly summarize what we learned about AXI till now. AXI is a high performance communication protocol used to transfer data between different components in a system. It uses independent channels for read and write transactions, and uses the valid and ready handshake to control every transfer. For write transaction, AXI uses AW, W and B channels. For read transaction, it uses the AR and R channels. AXI also supports burst transfer, where multiple data bits can be transferred efficiently using a single starting address. We learned about the 3 burst types: fixed, INCR and WRAP, along with important signals such as AWLEN, AWSIZE, AWBURST, write strobe, WLAST and RLAST. And that's the basic working of the AXI protocol. Thanks for watching. I hope this tutorial helped you understand AXI better. If you like this video, please subscribe my channel and comment below if you have any queries.